introduced the category of vertex algebras. So let me just start with a statement. So the theorem says the following. So you can indeed construct a functor. So this is conjectured by the people who introduced this 4D2D duality. So for any G, there exists a unique monoidal functor from the category of two-bodism to the category of vertex algebra I just introduced. Such that the following hold. So I didn't change objects, so I don't change the first condition. The circle has to go to this given G. And then the second condition is the same. The cylinder have to go to identity morphism in this category, which I'm going to explain later. Let me just write like this. So the statement includes the existence of this identity morphism. And the image of a cap is the Drinfeld-Sokolov reduction of this.
So this IDG is like a chiral differential operator?
Yeah, exactly. Yeah. G is some complex semi-simple group, algebraic group.
I have a couple of questions. So now all this is happening on an arbitrary level, or you need some specific level, need some
Critical level.
So everything only on the critical level, but in principle, but this algebras they're going to construct, they will. I mean, for example, when you write units of reduction, chiral differential operators, they live on arbitrary levels somehow. So somehow, in principle, is there a way to construct this algebras to extend this to a family of algebras over any level?
I don't think so, because this associative variety is symplectic. I don't know any way which has associative variety and has one parameter family.
Right, but maybe associative variety will change in this way. Okay, I don't know, but just all the examples you wrote so far, they live on, they exist for arbitrary level.
Yeah, but this composition can be only defined for.
No, this I understand, but somehow, but just everything which is written here makes sense for any level. Both, I mean, the two examples you have here is chiral differential operators and triple reduction, and both make sense for any level. So, well, okay.
I don't know. And moreover, we have So the statement either this diagram commutes. So we have and this is way to explain.
So I complex by definition is just a variety. So this is not there is no statement about scheme structure.
It's different as scheme. It's different as scheme. So this is reduced, but this is not reduced. As varieties.
It's a particular state that when you write these compositions on principle, there might exist homology at different degrees in a particular state, but homology is only one.
For genus 0, yes.
Only for genus 0.
Yeah. So let me first explain example before telling you the construction. For SL2, image of BFN functor of pants was C2 tensor C2 tensor C2. So this is the symplectic vector space, and natural quantization is a wide algebra. And the natural affinization of wide algebra is called beta gamma system. So yeah, it's not a reason, but so as is expected, this is a beta gamma system associated with a symplectic vector space. So in particular, this is a free field. And you recover this as associated variety. Now, it's more interesting to see what is the image of four boundaries. So the Higgs branch was minimal nilpotent oblique closure in D4. And we have seen this before. And so this is exactly the case I explained before. So the image of four boundary is simple affine vertex algebra associated with D4 at level -2. So theorem reproves the fact that the associated variety of this one is minimal nilpotent oblique closure. And for the relations, so this composition gave ADHM construction for minimal nilpotent oblique closure. So in the VOS setting, what you get is a kind of free field realization of this affine vertex algebra, because here we have a beta gamma system, which is free field, and beta gamma system, and you take a relative semi-infinite cohomology. This is a very non-trivial statement. And for G equals to SL3, BFN functor gives you for pants, minimal nilpotent oblique closure in E6. And this is again we have seen. And corresponding VOA is affine VOA of E6 at level -3. I forgot to say -2 is of course a critical level for SL2, and -3 is critical level for SL3. And theorem proves the statement that the associated variety of this is minimal nilpotent closure. But in general, there's no this kind of simple description, and general VOA are not really generated by the algebras, but it's generated by.
We just checking. We can see these distinct generators in some construction.
Yeah, we can
By hand.
by hand. Yeah. It's a fun to. I'll explain construction, but it's a fun to see how it works. You need some computer, but. So let me explain construction. Of the functor. So first I have to explain what is, it's already explained by Ivan, but I have to explain what is the identity morphism from G to G. So in the category of simplicity, it was cotangent bound to G. And natural quantization of this is differential operators on G. And there's natural affinization of differential operator on G, and it's called CDO, chiral differential operators on G. So this is introduced by Marikov and Shetman. Weintraub and Beilinson and Greenfield. For general smooth algebraic variety, but because G is affine, we identify we are considering global section of differential operators, and in this case it's easy to describe. In fact, it's just induced representation of affine Kac-Moody algebra, induced from function on this uniport on this group. So there's a natural. So K acts by K. So this is one parameter family of CDO, and GT acts naturally as, for example, left invariant vector field.
So this algebra should be understood like the inverse limit of some finitely generated algebras, right?
Sorry?
So
I'll explain what to think of this in a minute.
okay.
But first, let me explain how vertex algebra structure is described. You have a natural embedding from here to here. You just send f to one tensor f, and this one is so this is one can consider the infinite jet ski on G. So this has, in particular, this has commutative differential algebra structure, which is the same as commutative algebra. And this is embedding of vertex algebras. And also we have a natural map from VKG to here, which is also a vertex algebra home. So, and this generates this algebra, so I just have to explain the commutation relation between them. So I take generating field, and here generating field is FG, F, which sits inside the function on G, which is contained in G. And OPE between them is just this one. So this is action as a left invariant vector field. So this is very easy vertex algebra. Also, it is a very big vertex algebra. And so there's a left and a right action on G, and this upgrades to the action of affinely to commuting action on affinely algebra on G hat. So we have that embedding induces action of G hat at level K. And there's also a dual action at the dual level. The dual means K plus K star equals to minus 2 times H. So in particular, if both critical, both actions are critical. And we have, so this is compatible with the action structure of vertex algebra. So we have a vertex algebra map from here to here. And so if K is not critical, so you have a Sugawara operator here and Sugawara operator here, and the sum, so Sugawara operator for this one and Sugawara operator for this one defines conformal stress tensor here for non-critical level of central charge 2 times dimension of G. But at the critical level, each of this doesn't make sense, but the sum makes sense. And this is conformal for all level, including critical, and the central charge is 2 times dimension of G. And this is a simple VOA for any K. Now, so CDO in general should be thought as a replacement for the differential operators for the loop space. But in this case, it's literally true. So this means that the module over CDO is the same as module over D module on this loop group, if you properly make sense of it. So in particular, this means that if you consider a D module on the affine Grassmannian, this is equivalent to the category of CDO module, which are equivalent under the action, right action of GT. And the correspondence is that if you have a sheaf here, you consider a pullback and take global section. And the CDO itself corresponds to a delta function D module at identity.
When you say equivariant, it means strongly equivariant, right?
Yeah.
But the CDO itself is...
No, it's equivalent.
Okay.
Now, so you have I don't have a... So we can restrict this equivalence for GT equivalent D module on the Grassmannian, and which is the same as the category of Faber sheaves. No, what I want to say is so this is equivalent to the category of representation of dual group by geometric Satake.
What is your assumption of K?
I want to make it critical at the end.
Sorry?
Critical. I want to make it critical at the end.
You want to make
Critical.
critical?
Yeah. So let's make it critical. DG. So in this case, this is equivalent for the both action of GT. And this is not just equivalence of abelian categories, but equivalence for the tensor product structure. Here you have a convolution product, and it's natural to ask what is the operation corresponding to convolution product. And the answer is this operation I introduced. So it was explained in Frenkel category so this operation corresponds to convolution product is exactly this product. And as I said, so dg itself corresponds to a delta function which corresponds to C, which means that this is isomorphic to N. Here it comes from this category. And in fact, you can check that this holds for any objects in casuistic category. So you can check directly without using geometric Satake.
Sorry, F1N.
Sorry, N. So this shows that the dg minus hx is indeed identity morphism in this category. So we identified the identity morphism with CDO. So then automatically we get the VOA corresponding to the cap. So by action, so we get the image of cap has to be a Drinfeld-Sokolov reduction of this dg minus h chiral. But so this definition makes sense for any level and level any f. So let us define more generally Drinfeld-Sokolov reduction of CDO and call it equivariant affine double algebra. So we had this map, and we made a reduction with respect to the action of here. And so that this action remains on this equivariant double algebra. So we have a map from usual double algebra, tensor with Vk star G to this equivariant double algebra. Now, so you can check that the associated variety of this equivariant double algebra is in general equivariant Srodoi slice. And I didn't introduce those algebras, but let me just state this those algebra is finite double algebra introduced by Ivan, and which played an important role in representation theory of finite double algebra. And the usual double algebra sits inside equivariant double algebra, but as a commutant of this G hat. So this is exactly the commutant of this one. So this is a commutant or coset of Vk star G in equivariant double algebra. So this gives another definition of double algebra. And for any objects in Kazan-Lucy category, usual Donifield-Sokolov reduction functor can be replaced by the product with equivariant double algebra.
Sorry, this is for GC delays, right?
No, for all.
I mean, this is range or?
Sorry?
This theorem, is it true for any G or only for single delays?
For any G, for any F, and for any K. So if you extend the definition of product, this is just this one. And in fact, this gives better explanation of why associated variety has to be intersection with Srodoi slice. So, in particular, so eta G VOA. So this so this should be what? So this should be product with doing equivariant double algebra with this one, and this is Buddhism with this kind of boundary. So this has boundary. If this has boundary R, this has boundary R plus 1. So then what I want to say is this is Donifield-Sokolov reduction of so VOA associated with R boundary is obtained from R plus 1 boundary by a Donifield-Sokolov reduction. So what now? What do you want? So we just have to try to construct inverse functor to Dirichlet-Sokolov reduction. Then we get everything. So this is what I'm going to do. But first, let me recall this well-known theorem. So for critical level, the double algebra is the same as Feigin-Frenkel center. So in particular, it's a commutative vertex algebra, which is identified with the center of this vertex algebra. So this is a center of and in particular, associative variety and associative variety is therefore the same as adjoint quotient. So you have a generator corresponding to the generator of invariant polynomial. And corresponding degree is di plus 1, and di is exponent of G. So this is generated by freely. So we have two actions, but this one is commutative vertex algebra. So now, how to reconstruct, how to construct the inverse functor to Dirichlet-Sokolov reduction. So let me, I haven't defined yet, but so this is not definition, but so let's call VOA corresponding to P0R VR. Now we know that V2 is CDO. And V1 is equivariant double algebra. And we somehow want to recover everything from VR. So if this kind of thing is possible, it should be able to recover V2 from V1. So is there any way to reconstruct V1 from V2 from V1? So we have two commuting action of G hat at critical level, and here only have one commuting action of G hat. But so we want two commuting action of V2. So first thing to consider this tensor product. But this is not correct answer. There are several reasons. First of all, I forgot to say, but this equivalent double algebra is not positively graded. the conformal weight is not bounded from above. So this is not positively graded, but this one is. So this cannot be isomorphism. And another reason is that we have a CDO we have this vertex algebra homomorphism, but this map is not injective. So recall you have a map from UG to UG to differential operator to G, and this map is not injective. And the kernel is generated by the center. So it's factored through this embedding. And similar situation holds for this case. So this must factor through this tensor product. And this is the only relation. So you somehow want to identify this action of the center here and action of the center way here. And there's a natural way to do so. So namely, we can consider following a BRST reduction. So we consider V1 tensor V2, and we consider action of the center, so something like this. And so we want to make this action 0. So what we do is we just take a corresponding BRST cohomology by considering this as a commutative Lie algebra. So more precisely, this is H0 of V1 tensor V1 tensor fermions, so Psi tensor product of fermion generated by Psi and Psi star, and with BRST operator, where BRST operator is defined as Pi G tensor 1 minus Pi 1 tensor Pi G and Psi star G. And because it's commutative, Q0 square equals 0, and this defines a cohomology. And again, it's defined by BRST cohomology. This has a structure of vertex algebra, and the action, you can identify action of the center here and action of the center here by definition. And miraculously, this construction works. So you get the right object by defining this. So this cohomology, zeros cohomology, is in fact V2, which is a CDO as a critical level.
So this is only for this choice of E1?
Sorry.
Or so this only, I mean, at some point you said that you want to construct a functor, which is inverse representable reduction.
Yeah, it's not the functor yet, but you can define. Yeah, so functor is defined into And I applied
From where to where? So it's
from the category of module of Eigenfrankel center to the category of G-hat module as a critical level.
And is there a reason why you take only zero homology?
Because we don't have vanishing.
For any L?
We have vanishing of negative degree, but it's not so bad. Yeah, I said miraculous because we don't have vanishing.
And it's really not true. So, I mean, reciprocity is V1 times V1. Is there, do you know if there is high homology?
Sorry?
I mean, in this line of streams, so they agree with V1 times V1, and then this homology, is there a high homology?
There is a higher cohomology. Yeah, so this is first statement. So more generally, so if you consider this functor in general, for casuistic category. So you recover, you can go back to M by considering this procedure. Sorry, I cannot hear.
What?
Cannot hear.
V2 is identity in your category.
V2 is identity, yeah.
How does it compare to this problem?
V2 is Donifer-Sokolov reduction of V2, which is V1. So V2 is cylinder. So you can cylinder. You can get cylinder by considering cap and let them talk each other through Eigenfrankel center. And if you want to do the same for a punch, you can consider 3 caps and let them talk, or you can consider cylinder and talk here, and the statement that we get the same, all get same. So we can define VR in one of the way. So let us define like this. So I'll consider action of the center corresponding to, I know, I think you know what you mean. Okay. And the theorem is that this in fact gives satisfies the desired property. So I already explained in the picture, but let me state. So we have the associativity isomorphism. So of this associativity. And VR is simple and conformal. And central charge is R times dimension of G minus R minus 2 times rank of G minus 24. So, check. And this was the dimension of the Mowa-Tachikawa variety. So this is negative for if R is bigger than 3, I think. And you can also describe the character. So it also gives a different expression of modules such as L minus 2 for D4 and L minus 3 E6. So this is a wire module. So this is explicit character formula for the VR. And finally, the associated variety is isomorphic to the Mowa-Tachikawa variety. Any question?
Somehow said that if you go beyond genus 0,
Yeah.
some kind of expansion.
Yeah. For example, if you consider torus, so this is what? You consider Hamiltonian reduction with respect to the adjoint action of G, but this is not, moment map is not flat.
It's not what I'm saying.
Moment map is not flat. I don't think.
Well, but is it somehow, even though, yeah, I mean on the level of vertex algebras?
In the level of vertex algebra, you really have to consider higher cohomology. It's some super vertex operator algebra.
And this gluing procedure for this trace, what does it mean? Do you have some structure which you can multiply some traces and integrate some variables and give new character, yeah?
What?
No, this procedure when you glue surfaces, to what it corresponds for characters?
You can accept as some integration. Yeah, there's formula by physicists, so you can have a look.
have to